There were some sort of major new directions. There were some minor fixes and then some little details. So the sort of in the major features are the things that we've talked about. The non-blocking collectives we've talked about in the section of this course on collectives rather than deferring it to an MPI-3 section. It's just a different way of organizing things. Same with the neighborhood collectives and one-sided to some extent, although we didn't do all of the new things in one-sided. There's a new tools interface that goes beyond the PMPI profiling interface, which I will say a little bit more detail about. And we have new bindings for Fortran that fit with beyond Fortran 90 and make use of some of the new features in Fortran 2008. It's one reason for opening up the form process again. And then there are some sort of minor bits that are affecting a small number of functions. One of the things that we didn't get right was thread safety of probe. So receive is supposed to receive the last message that was returned by the probe, but what if one thread does the probe, or multiple threads do a probe and another one does a receive? Which message are you going to get? So that's been cleaned up. Creation of communicators at large scale. Communicators it used to be a collective operation, now there's a non-collective version. So that's an addressing of scalability issues. People are now used to having the official bindings for subroutine calls. If something is a const, then we now have declared it to be a const, so that helps the compiler detect incorrect calls. There's a new way of creating communicators with where you split on the type, and a few other data type functions. One thing we did was remove the C++ bindings. They were introduced in MPI-2 and then not really used very much. That is, in MPI-2 we wanted to address MPI usage by C++ programmers because C++ was really moving into HPC in a way that it hadn't at the time of MPI-1. And there are sort of three options. We could just, since you can call C functions from C++, we could just use the C bindings, that is, not do much of anything. Or there could be a real object-oriented library of the, that was very C++-like. The C++ bindings in MPI-2 are sort of a middle ground. So you now do a send operation becomes a method on a communicator. You do communicator.send. And so it preserves the correspondence between the C++ calls and the C and Fortran calls, just like the C and Fortran calls all match up. But it doesn't go all the way to what people would really like. And there were a couple of experiments. There was a library called MPI, was that the name of it? The object-oriented MPI that Jeff and Andrew did. But we decided to take this middle ground. Well, it turned out that meant that people didn't really use it very much because they didn't get enough benefit beyond the C++ bindings, and it did make things more difficult for implementers, especially as the number of MPI functions grew. So the MPI-3 forum decided to remove the C++ bindings. So if you're a C++ programmer, you just use the C bindings. And there were a number of functions that were deprecated in MPI-2. What that means is that in MPI-2 we found a better way to express that function with a better arrangement of arguments or something that we'd rather have done it that way. So we, in wanting to preserve complete backward compatibility from MPI-2 to MPI-1, we added the new better function but left the old one there and deprecated it. That is, advised users not to use that old one. So MPI-3, those deprecated functions are removed. So there's not perfect backward compatibility from MPI-3 to MPI-2. The incompatibilities we've tried to minimize to a great extent, but the old deprecated functions are actually gone now, and in a compliant MPI-3 implementation, they're not there. Non-blocking collectives is what we've just been through this afternoon in some detail. They're non-blocking versions of all the collective calls. They return requests, just like the non-blocking point-to-point, have to be completed with test or await. And as Rajiv was explaining, you can have multiple ones outstanding at the same time, but they have to be called in the same order. The neighborhood collectives are, the neighborhood is sometimes also called sparse collectives. So they're a response to the scalability requirements. So some of the, as Rajiv was saying, some people would kind of simulate neighborhood collectives by calling things like all to all with mostly zeros in the spots where you say how much data, all to all V, where you leave zeros in the spots that say how much data is communicated. But you have to have that slot there in the array that you pass to the MPI call for as many processes as you have, because you have a length for each process. And if you have 10,000, 100,000 processes, then you're passing a gigantic array, and in some of them you're passing quite a few of these arrays just in the parameter list. It's a scalability problem in the specification itself, as well as it forces non-scalable implementations. So as Rajiv has just been explaining, now you just need to pass to these neighborhood collectives the data that they need in order to do what you want them to do. So earlier today, when we were talking about RMA in general, we talked about some of the additions in MPI-3 that have been made just for MPI. So there are new ways to, for MPI-3. So there are new ways to create windows. There is a way to allocate a window that can then be used as a area of memory that's actually shared among the processes that multiple threads could use or multiple processes could use. And then there are the new read, modify, write operations. These were the things that should have been in the MPI-1 or the MPI-2 original one-sided operations, because they're the things that people want to do with shared memory. So there's a new unified memory model that lets you address more directly the shared memory that you might have on the machine. We won't go into much detail on that. And then there are these new versions of put, get, and accumulate that return requests, so that they've always been non-blocking, but now they're non-blocking in the very same way that the send and receive operations are. So it's another way to complete requests, to complete one-sided operations besides the fence, the post-start complete wait, and the lock unlock. For tools, there's a completely new approach to an interfaced MPI for building tools. Way back in MPI-1, we thought about building into the spec certain requirements for tools, but tools tend to be very specific to implementations. And so MPI-1 had this idea of the profiling interface, which most of you are familiar with, where it allows any tool builder to intercept MPI calls and do things with them without ever touching the underlying MPI implementation. So this is I thought it was a cool idea, and it's meant that a lot of MPI tools have been built that way. But as we try to get performance on these very large scale machines, and we have very much larger scale MPI programs, people have found that they really want to know what's going on inside the implementation. So the profiling interface from MPI-1 sort of by definition refuses to tell you anything about what's going on inside. It lets you time things, and everything that you can observe from outside, there's a way to intercept and report, but what's going on inside the implementation is opaque. And the tricky part of this is that the different implementations have different structures inside, and if you're trying to debug something on a blue gene, for example, you might want to know things about how the network is performing, or how the MPI implementation, what its data structures are looking like, and you might want to ask questions that don't make any sense on a Cray, because it has a different set of things that are critical for performance. So the tools interface lets an implementation publish the things that it wants to publish, and lets the application or the tool writer find out what those things are, and then query the system to find out the answers of those things. So an example of the sort of thing that you might want is the following. And this involves an application that I was working with a physicist on. And Many applications, this has come up once or twice when we were talking about details, have some internal data structures that where for something that is usually called the unexpected message queue. So if a message arrives that there's no receive for, the system has to remember that stuff because the receive is going to be posted later. So it's going to stash that in some data structure, and since we don't expect it to be very long, we might keep it in a linked list or something like that. So what was happening in this particular application is, well, things were bogging down, and we began to wonder whether there were a lot more unexpected receives piling up at certain nodes who were not getting around to receiving them than we expected. You know, you have your program and you have a model in your head of what's happening while the program is running. What tools often tell you is that it's not doing that, it's doing something else. That was the case here. We found out there's a very special way to dig inside the IBM implementation and ask how long this, and find a header to this queue. And since we had the source code, we could write the code that runs down this queue and sees how long. And there were 30 to 50,000 unexpected messages sitting on this node. And of course, for every time a receive was posted, process had to run down this linked list looking to see if the message that it was looking for was there. And if it wasn't, of course, it went all the way to the end. So it was showed that we had a badly designed program instead of getting our receives posted ahead of time for the sends. So in the future, the next implementation, IBM will be able to publish that, or essentially making available a routine that you can call. Now, some other implementation might not have anything like an unexpected queue. They do something completely different. But the tools interface allows a portable way, sort of it's a compromise, a portable way of querying what sorts of things you can find out and then finding those things out. So it's a help for primarily for tool builders who are doing profilers and things like that. So Fortran has changed since Fortran 90, and Fortran 90 had some things that didn't fit well with MPI. MPI doesn't. Fortran 90 has more type checking, but MPI wants to be strictly compliant. An MPI program would have to have different MPI sends for every different data type, or you would have to use a Fortran 90 module that had a gigantic number of prototypes in it. So now things work better together, and modern Fortran compilers will do type checking for MPI arguments. Also allows one to pass array subsections, which wasn't possible before. And the IR option, which is often ignored, often forgotten about by Fortran programmers, is now optional. And there are quite a few other problems that existed that have been tidied up. So we mentioned these things all already, really. Okay. There are a couple of things that the MPI forum discussed a lot, and there were proposals, and there were debates, and there were votes, and in the end, the forum decided that they were not ready yet. So there was a lot of discussion of fault tolerance features, exactly what that should mean, what MPI could do about it, what the API for doing those sorts of things might be. Fault tolerance is a tough problem because it affects all aspects of the computation, not just the MPI library, but maybe MPI could be helpful to the other parts in creating an integrated solution, or at least an approach to fault tolerance. That turned out to be, I would say, too complicated, and the proposals didn't end up getting the required votes. There was a more detailed approach to hybrid programming. Bill is going to talk on Thursday, I believe, about hybrid programming. So there were proposals that would let you send messages that were targeted to specific threads or specific endpoints that they were called, and one dynamically attached threads to endpoints, and this let you program some of the new multi-threaded machines in great detail, and the forum, in its wisdom, decided this was not quite ready for prime time. But these sorts of things may be may be picked up in a future version of MPI. And MPI is going to continue to evolve. If you're interested in participating in the MPI looking forward, the MPI process is still a completely open process as it was in the beginning. Anyone can participate who wants to. You can track it passively by going to this website. The forum posts minutes of its meetings and its intermediate documents, and you can see what the forum is doing and certainly comment. The current standard and as it is now can be found at this website. And if you would like to actually come to meetings, that can be arranged. So that's it for the presentation part of